Cool. Take a second here. Here's a multiple choice question, even though I'm not a big multiple choice guy. Look at that synthesis reaction. Look at that equilibrium constant, and then tell me which would it be at, which is in the higher concentration equilibrium out of those three things. Who's going to have the highest concentration once equilibrium is reached? All right, look at that equilibrium constant, 10 to the 83rd. That's a number that's essentially infinity, right? I mean, you can't, I can't imagine a number that big. I mean, Avogadro's number is 10 to the 23rd, and that's too big a number to possibly comprehend. This is 10 to the 83rd. That's insane. Product side are insanely favored. So the highest concentration is going to be the H2O, which was letter C. There would be like no reactant left. This is going to go all the way to the right, and it's going to heavily favor the product side. Cool. Great. I love these questions. Okay, we're not taking the ACS final here in the summer, but if you're taking this during the spring or fall, which I guess Chem 102 is spring, the ACS final loves to do questions like this where they're pictures and you got to try to like decipher the picture, right? Because they're testing your skills to be able to read a graph and read pictures. Anyway, we got a rearrangement here. A is rearranging into B, and this reaction is an equilibrium constant of 2. The question is, which of these boxes, box 1, box 2, or box 3, would represent this reaction if it at equilibrium, if the equilibrium constant is 2, where A is red circles and B is black circles? Take a second, look at it, and we'll talk about it. See if you can't figure that one out. I love that question. So we can kind of take the number of circles and use that to, figure out the concentration of each. So at the end of the day, first thing we should do is write a mass action expression. So my mass action expression is going to be the equilibrium constants equal to the concentration of B, which is my product, to the first power, okay, divided by the concentration of A, my reactant, and then that's also to the first power. So now we're going to plug some things in. For this first one, that would be 3 B's, because those are the black spheres. So 3 over 3 A's, because those are the red spheres. And that first box is showing, if that reaction is at equilibrium, that's showing a reaction that has an equilibrium constant equal to 1, which is not 2. So it's not that guy. Let's do reaction 2. Here we have 6 B's, and we have 3 A's, and this is going to be your winner. 6 divided by 3 is 2. That one is representing an equilibrium constant of 2. Here we have 3 B's and 6 A's. So this is going to be the inverse of that, right? This would be 3 products, 6 reactants. That would be 0.5. Whoops, 0.5. So that is obviously not it. The answer is reaction 2. All right. So let's change things up. It doesn't look like anything changes here on this slide, but it did. Now I've got a 2 here. I want you to take a look here. Write the new mass action expression if A rearranges into 2 B's. Really, I guess that'd be a decomposition, right? Okay, if A is turning into 2 B's, write the new mass action expression and see if which one of these reactions, if any, okay, would represent an equilibrium constant of 2 now. Go ahead, try it out. So now we're going to write a new mass action expression. The mass action expression now is Kc or Keq equals the concentration of B squared divided by the concentration of A. And now we're going to punch some stuff in here. So for B, that would be reaction 1, that would be 3 squared over 3. That's 9 divided by 3. So, 9 divided by 3 is 3. So that is not 2. It is not reaction 1. Taking a look here, reaction 2, that would be 6 squared over 3. That's 36 divided by 3. That's 18, I believe. So not reaction 2. And here we would have 3 squared over 6. So that's 9 divided by 6. That's 1.5. And it depends. Are we rounding up, right? What are we doing here? If we're rounding up and you circled reaction 3, sure, right? I mean, that only has 1 sig fig, right? So, reaction 3. If you got 1.5 and you said none of them, that's fine. You had the right thought process, right? You just didn't round up to 2. So, you gotta, again, what did we do? We wrote the new mass action expression. This has now got that one product squared, okay? And yeah, plug it in. Good stuff. Take a look at these. Which of these statements is false? Take a minute, read through them, really think about them, okay? And we'll talk about it. So which of those statements would be a false statement? If you look at the top one is 100% true. If the equilibrium constant is way greater than 1, the forward reaction is favored and essentially goes to completion, and it's all products. So it is not A. Taking a look at B, B is also 100% true. Okay, if the constant is way less than 1, then essentially the reverse reaction is favored. It is all reactants, very little products. So B is true. In C, if the equilibrium constant is close to 1, neither side strongly favored. That is 1,000% true. So D must be and is our false statement. If the equilibrium constant is much, much greater than 1, that implies the reaction is fast. All that and this is a misconception people get into all the time. If that equilibrium constant is much, much, much greater than 1, all that means is that whenever that reaction gets to equilibrium, it could take 2 minutes, right, or 2 million minutes. But whenever it reaches equilibrium, you're going to have a lot of products, very little reactants. It tells you nothing about the speed. Kinetics and equilibrium are two totally different things, and you got to study them separately. Cool. Okay, so now what I want to do is I want to talk about the relationships between the equilibrium constant with the forward direction and the reverse direction. So what do we have here? Okay, we have in A, we have two SO2s and an O2 making two SO3s, and in B, we just wrote the reaction backwards because where two SO3s is breaking down into two SO2s and O2s. Here, the reactants became the products, and the products became the reactants. Okay, now. Okay, people always say to me, they say, wait a minute, if a reaction is reversible, if reactions can go backwards, right, and products can turn back into reactants, then why does it matter which way we write the reaction? Well, the answer is it doesn't. Okay, you can write a reaction either way, okay? But if I know the constant, if the reaction is written this way, then the equilibrium constant, if I write the reaction the other way, is going to be the inverse of that. And I want to prove that. Here's what I want you to do. I want you to, let's first start by you writing the mass action expression for A and the mass action expression for B. And then we'll plug some numbers in there. So I'm going to do the same thing on the board back here. Start by writing the mass action expression for reaction A, and then write the mass action expression for reaction B. So hopefully here's what you got. Products over reactants, product coefficients become exponents. So make sure that you got those in there. These two are just the inverses of one another. Now I want to prove that mathematically. When this reaction reaches equilibrium, here's what happens. You will find, if you let this reaction reach equilibrium, okay, you would find that maybe the SO2 concentration is 0.0030 molar, the O2 is 0.0035 molar, and the SO3 is 0.050 molar. Here's what I want you to do. I want you to plug these values into both of these mass action expressions. And I want you to calculate the equilibrium constant if you wrote the reaction like it is in A. And I want you to calculate the equilibrium constant like if you wrote the reaction like it is in B. And then we're going to compare them and really prove that they are inverses. So go ahead, I'll give you a head start, and then I'll plug the numbers in too. Again, it's just practice and putting it in your calculator correctly, right? Do you know how to use parentheses for the stuff? Right. So let's do this. In the top one, 0.05 squared divided by the quantity 0.003 squared times 0.0035. And we get 79. I'm not going to worry about sig figs here. I'm just going to take over the ones place. 79,365. Technically, it'd be 79,000, right? Then here, we got 0.003 squared times 0.0035 divided by 0.05 squared. And we get 1.26 times 10 to the negative fifth. So what are the relationships? Well, obviously, hopefully you can see this. These guys are just flipped. So let's prove this. Here should be the relationship. The equilibrium constant for the forward reaction, we'll call this one the forward reaction, should equal 1 divided by the equilibrium constant for the reverse reaction, for the opposite direction. So let's prove that. Doesn't matter which. Okay, let's do 1 divided by 1.26 times 10 to the negative fifth. And if we do that, we should get, okay, 1 divided by that number should give us the 79,365. So we're taking the inverse of this number, and we do indeed get that. Now, another option, instead of doing 1 divided by, you could raise the whole thing to the negative first power. That's that x minus 1 button, okay, that you might have on a TI 83 or 84. It's below the math button. Okay, raising anything negative first power is the same as taking the inverse of it. So what we just got is a very important relationship. It doesn't matter how you write a reaction technically, if reactions are reversible. It's just if I know the constant for one, you got to do the inverse if you're going to write it in the opposite direction. So that's what this top equation is showing right here. The forward reaction is equal to 1 divided by the constant for the reverse reaction. And we just proved that. There is another, I have never had to do this, but there has got to be a reason that you would. And it does tend to show up on, again, you guys aren't taking in the summer, we don't take the ACS final, but if you're taking this in the spring, it does tend to show up on ACS final exams. For some reason, it's kind of like Hess's law, where if I were to, distribute like a 2 into here, right? I was going to multiply everything by 2. So 2a, 4b, and 6c, okay? What would be the equilibrium constant now? How would that be affected? Well, whatever you're distributing in, you raise the constant to that power. So say that this normal reaction had an equilibrium constant of 4. If I distributed a 2 into there, that would now be 4 squared. This would be 16. I have never had to do that, but there must be some reason that you would, because this is in like every textbook, and I've seen it on ACS tests. So I just, in all of my research and doing actual chemistry, I have never needed to do it. I'm sorry, I can't tell you. I haven't been able to find a use for that, but it's a thing. So there you go. This one I have had to do, and you might have to do in the acid-base chapter. If I have a diprotic acid that gives off 2 acidic hydrogens, we can get the overall equilibrium constant for a multi-step reaction. Here's what I mean. And again, this is kind of like Hess's law, okay? If I have A turned into 2B, but then the 2B turns into 3C, okay? This would be that reaction intermediate thing where it's made and then used up. Okay, the net reaction would be A goes to 3C. Well, if I know the equilibrium constant for each of these individual elementary steps, I can get the overall rate constant by just multiplying them. If it was a 3-step reaction, you just multiply K1 by K2 by K3, and you would get the new overall reaction. I have had to do that one. Okay, so the overall rate constant for a multi-step reaction with multiple elementary steps, you just multiply each individual rate constant. Cool. So let's try and apply that knowledge. Same thing here, but a little different. I know the overall rate constant and the rate constant for one of the elementary steps. Can you get the other elementary step? Think about it. Give it a shot. All right, so this guy should be pretty easy. Here's what you got. It's really 59 times x equals 478. So 478 divided by 59, 478 divided by 59, 8.10. This second reaction must have an equilibrium constant of 8.1 because 59 times 8.1 is that 478. There we go.